Hello there, and welcome to the Sleepy Scientist. Tonight, we drift toward a world that glows like an ember in the dark, a planet wrapped in mystery, veiled in shimmering layers of cloud light, and shining brighter than anything else in our night sky. This is Venus, familiar yet distant, beautiful yet unreachable, ancient and endlessly intriguing, quietly inviting you to leave the weight of the day behind. As we begin, take a moment for yourself. If you'd like, gently close your eyes and let your shoulders loosen. Let your breath settle into an easy rhythm, each inhale softening your thoughts, each exhale letting the noise of today fade into the background. Whatever rushed, demanded, or interrupted, you can drift away now, slipping to the edges of your awareness where it no longer needs your attention. Imagine the soft glow of Venus rising into twilight, not harsh, not hurried, but steady and calming, like a lantern suspended above the horizon. Beneath that glow is a world moving in slow, ancient rhythms. A day lasts longer than a year. Clouds sweep around the planet in smooth, unbroken currents, and sunlight diffuses through the atmosphere until the entire sky seems to glow from within. Venus exists in a state of quiet continuity, where time stretches gently, and every motion unfolds with serene patience. So allow your thoughts to fall into that calm rhythm. Let the glow of Venus soften your mind and guide you toward rest. Let's begin deep within the quiet glow of the evening sky. Venus reveals itself as a world where the rules of time unfold differently from anything we know. While Earth spins through a full day in just 24 hours, Venus turns so slowly that one rotation lasts longer than its entire year. If you could stand on its surface, the sun would take months to rise, drift slowly across the sky in a long, unbroken arc, and then months more to set. The entire sky would seem to move in a dreamlike motion, almost as if time itself had softened. This slow turning shapes everything on Venus: the winds, the temperature, the light, creating an atmosphere that feels suspended between moments, as though the planet exists in a calm, extended breath that never fully ends. High above the surface, Venus is wrapped in a blanket of clouds, thicker than any found on Earth. Clouds so dense and reflective that sunlight barely reaches the ground. These clouds are not simple wisps. They form a continuous veil stretching across the entire planet, glowing softly as they catch light from the sun. They swirl in immense, planet-sized patterns that move far faster than the surface below, creating a graceful dance of motion that circles the globe in just a few days. From above, the cloud tops appear smooth, luminous, and almost fluid, like a sea of pale gold shifting in slow waves. This cloud deck is what makes Venus shine so brightly from Earth, acting as a cosmic mirror reflecting sunlight with such efficiency that the planet becomes the brightest natural object in our night sky after the moon. The winds that sweep through Venus's upper atmosphere move with astonishing speed, reaching hundreds of kilometers per hour. Yet when seen from afar, their motion appears incredibly smooth. There are no violent storms or chaotic breaks in the pattern. Instead, the winds wrap around the planet in a steady, unbroken flow, carrying the entire atmosphere with them like a continuous tide. This phenomenon, known as superrotation, means that while the planet itself turns slowly, the air above it moves swiftly enough to lap the planet over and over again. The effect creates a surreal contrast, a world where the ground lies nearly still, while the skies swirl in graceful, high-speed currents, giving Venus an inner stillness and an outer motion that blend together into a tranquil, otherworldly balance. Because of Venus's thick atmosphere, sunlight does not behave the way it does on Earth. Instead of shining directly onto the surface, light becomes diffused through layers of cloud and gas, transforming harsh rays into a soft, uniform glow. Standing on the surface would feel like being inside a glowing fog, where there's no clear source of brightness, only a warm illumination filling the air from every direction. Shadows would be faint and blurred, and the horizon would appear hazy, making distance difficult to judge. This soft light contributes to the planet's dreamy appearance, giving Venus a timeless, suspended quality that feels almost like standing inside the memory of a sunrise rather than witnessing one directly. The surface of Venus, though hidden from view, is a landscape shaped by gentle but immense geological forces. Wide volcanic plains stretch across much of the planet, interrupted by smooth, rounded mountains and long, flowing channels carved by ancient lava. Unlike Earth, Venus does not have active plate tectonics, so its terrain forms slowly through gradual uplift and volcanic resurfacing. These landscapes evolve over millions of years in quiet, patient cycles, creating broad, softly contoured features that ripple across the surface like frozen waves. There are no sharp peaks or jagged cliffs dominating the terrain, only smooth rises and expansive plains shaped by deep, steady processes that unfold without rush or interruption. One of the most calming features of Venus is the way it reflects sunlight. Because its clouds are so thick and bright, they scatter sunlight across the entire surface of the planet, creating a consistent, gentle illumination. From space, Venus appears almost perfectly smooth in brightness, lacking the dark patches and contrasting colors seen on Earth or Mars. This uniform glow gives Venus a serene presence, as if the entire planet were enveloped in a soft, diffused halo. The reflectivity known as albedo is among the highest of any object in the solar system, which is why Venus stands out boldly in our sky, glowing with a steady, peaceful brilliance that never flickers. Venus experiences a phenomenon called retrograde rotation, meaning it spins in the opposite direction of most planets in the solar system. If humans could stand on the surface long enough to observe a full cycle, the sun would appear to rise in the west and set in the east, a complete reversal of what we experience on Earth. This reversal adds to the planet's dreamlike nature, making the flow of time feel inverted and unfamiliar. Combined with the planet's slow rotation, this backwards day creates an otherworldly sense of calm, as though Venus moves according to its own ancient rhythm, independent of the rest of the planets. High in the Venusian atmosphere, about 50 kilometers above the surface, conditions become surprisingly Earth-like. The temperature cools, the pressure drops, and the air becomes more stable. If a human could drift at this altitude inside a protective vessel, they would experience temperatures close to room temperature and pressures similar to what we feel at sea level. This region, often called the habitable layer, floats between the harsh surface below and the luminous clouds above. It is a place where sunlight filters through gently, winds flow steadily, and the planet's beauty can be observed in its purest form, a calm, serene layer, suspended between extremes. The clouds of Venus contain tiny particles that scatter sunlight into soft, pearlescent colors. While the planet appears bright white from Earth, the upper cloud layers contain subtle hues, faint yellows, soft creams, and hints of pale gold created by sulfuric compounds suspended in the atmosphere. When sunlight passes through these layers, the colors blend and shift gently, creating gradients reminiscent of glowing marble or diffused amber light. These quiet tones lend Venus a warm, inviting radiance, making it appear both gentle and luminous despite its intense environment. Venus has no moons, no natural satellites orbiting it, which gives the planet an unusual sense of solitude. While Earth hosts a large, bright companion, and Mars has 2 small moons, Venus drifts through space alone, without another body tugging at its tides or reflecting its sunlight. This solitary nature adds to its calm, self-contained presence a world moving through the solar system in stillness, carrying its own glow, its own rhythm, its own quiet identity. Deep within the heavy atmosphere of Venus lies a pressure unlike anything found on the surface of Earth. The air presses downward with a force equivalent to being far beneath an ocean, creating conditions where even solid materials behave differently than they would under lighter pressures. Despite the intensity, this pressure remains remarkably uniform across the entire planet. There are no sharp fluctuations, no sudden drops, no violent shifts. Instead, the atmosphere sits in a stable, almost balanced state, its weight spread evenly across the surface. This steady pressure contributes to the stillness of Venusian landscapes, shaping a world where everything feels slow, dense, and deeply settled, as though the entire planet rests beneath a quiet, consistent blanket of air. Hidden within the atmosphere is a greenhouse effect so powerful that it traps nearly all heat that reaches the surface. The thick carbon dioxide envelope holds infrared radiation with exceptional efficiency, causing temperatures to remain high regardless of location, altitude, or time of day. Unlike planets where temperature rises and falls, Venus maintains a constant thermal environment with only minimal variation. This stability makes the planet feel suspended in a long, unchanging moment, a world where warmth is not a cycle, but a permanent state. The atmosphere redistributes heat evenly, preventing the extreme temperature differences that occur on many other planets. Everything on Venus, from volcanic plains to distant highlands, exists in this same warm equilibrium. Although the surface of Venus is hidden beneath clouds, radar imaging has revealed a variety of volcanic structures that shape the planet's landscape. Among these are immense shield volcanoes, broad, gently sloping mountains formed by continuous lava flows. Their size is vast, stretching across hundreds of kilometers, yet their slopes rise so gradually that they appear smooth and rounded. The flow channels that wind across the surface also tell a story of past heat, showing paths carved by lava that once moved slowly across the plains. These channels can run for hundreds of kilometers, longer than any known on Earth. Together, these features create a terrain formed by long, steady processes rather than sudden eruptions, reflecting the calm, patient geological history of the planet. In the polar regions of Venus, the atmosphere forms enormous swirling vortices that rotate around each pole in complex, evolving patterns. These structures are not chaotic storms, but organized systems shaped by the flow of heat in the atmosphere. Their centers sometimes split into double patterns, creating a shifting shape that changes gradually over days and weeks. The vortex draws air downward, redistributing heat from the upper layers into the deeper atmosphere. Despite the movement, these vortices remain stable and persistent, continuing their rotation year after year. They are among the strongest and most enduring atmospheric structures on Venus, yet they move with a softness that matches the planet's quiet rhythm. The chemical composition of Venus's atmosphere includes sulfur dioxide, a gas that plays a major role in forming the planet's cloud layers. When sulfur dioxide rises to higher altitudes, it interacts with sunlight and other chemicals, creating sulfuric acid droplets that populate the clouds. This cycle of rising gas, transformation, and descent continues slowly and consistently, shaping the upper atmosphere in a predictable rhythm. Over long periods, the amount of sulfur dioxide observed in the atmosphere fluctuates, hinting at possible volcanic activity deep below the clouds. These variations are subtle and gradual, blending smoothly into the chemical cycles that define the planet's atmospheric behavior. A unique characteristic of Venus is the absence of a global magnetic field. Unlike Earth, which is surrounded by a magnetic shield generated by its rotating core, Venus produces only a weak induced field created by interactions between the solar wind and its upper atmosphere. Without a strong magnetic shield, charged particles from the Sun interact more directly with the planet, shaping the upper atmospheric layers and contributing to the slow loss of certain gases over time. Despite this vulnerability, the dense atmosphere protects the surface from harmful radiation, absorbing much of the incoming energy before it descends. The result is a planet with an exposed, evolving upper atmosphere, but a deeply shielded surface environment. The highland region, known as Ishtar Terra, contains Maxwell Montes, the tallest mountain on Venus. Rising higher than any peak on Earth, this massive formation sits within a landscape shaped by intense pressure and slow geological uplift. Radar imaging reveals its slopes in detail, showing ridges and plateaus that extend outward like the frozen waves of an ancient collision. The mountain's height stands out in stark contrast to the surrounding plains, yet its presence feels calm rather than dramatic. Nothing on Venus erodes quickly, so mountains maintain their shape for long spans of time, their contours changing only through deep, slow internal processes. Another major highland region, Aphrodite Terra, stretches across the equatorial zone. This vast area features rift valleys, volcanic structures, and long fault systems that give insight into the planet's interior forces. The terrain here is marked by broad, shallow depressions and raised plateaus, created by the slow movement of Venus's crust. Without plate tectonics, these structures form through gradual deformation rather than shifting plates, creating landscapes that evolve gently across millions of years. Aphrodite Terra, with its enormous size and varied topography, represents one of the most complex and intriguing regions on the planet. The atmosphere of Venus hosts waves and oscillations that travel across the cloud layers in steady, rhythmic patterns. Some of these waves stretch across thousands of kilometers, forming large-scale structures known as atmospheric gravity waves. These features help transport energy and momentum throughout the atmosphere, contributing to the super-rotation that drives the high-speed winds. The waves move slowly and consistently, revealing a dynamic but gentle atmospheric system that maintains balance through continuous flowing motion. Observations of these waves offer valuable insight into how the Venusian atmosphere remains stable despite its density and heat. Venus orbits the Sun in a nearly perfect circle, resulting in minimal variation in the amount of sunlight it receives. This circular orbit means the planet experiences no meaningful seasons, no significant shifts in temperature or atmospheric behavior throughout the year. The stability of the orbit contributes to the planet's consistently warm and uniform climate, reinforcing the sense of a world where change unfolds slowly. The absence of seasons adds to the timeless quality of Venus, where the passage of months and years brings almost no variation to the environment. Deep within the lower atmosphere of Venus, temperatures and pressures combine to create an environment where gases move with remarkable stability. The dense carbon dioxide behaves almost like a slow-flowing ocean of air, carrying heat evenly across the entire planet. Because there are no strong pressure differences and no rapid shifts in temperature, the lower atmosphere circulates in a steady, controlled way, creating gentle, long-lasting currents that move far more smoothly than the turbulent systems seen on Earth. This constant and balanced movement prevents extreme weather near the surface, allowing Venus's lower atmosphere to exist in a calm, uniform state that remains largely unchanged over immense spans of time. Radar imaging has revealed unusual circular features scattered across the surface of Venus, often referred to as coronae. These broad, ring-like structures form when hot material from the planet's mantle rises upward, lifting and stretching the crust before sinking back down. The process happens slowly, creating gentle domes surrounded by fractured edges that trace wide, rounded patterns. Corona vary in size, but often span hundreds of kilometers, making them some of the largest geological features on Venus. Their smooth, circular outlines and subtle internal deformation hint at deep processes within the planet, movements of heat and rock occurring far below the surface in a quiet, persistent rhythm. The atmosphere of Venus contains a distinct layer known as the unknown ultraviolet absorber, a region that darkens certain areas of the clouds when observed in ultraviolet light. The exact chemical responsible for this absorption remains unidentified, making it one of the longest-standing mysteries about Venus. This absorber affects how sunlight interacts with the cloud tops, shaping patterns and contrasts that shift across the planet. Although the material causing the darkening has not been confirmed, its presence plays a role in regulating the planet's energy balance. The steady patterns created by this absorber reveal atmospheric motions that would otherwise be invisible, allowing scientists to trace the pathways of winds and temperature changes within the upper clouds. One of the more subtle features of Venus's atmosphere is the gradual loss of hydrogen over long periods. Because the planet lacks a strong magnetic field, solar radiation interacts with the upper atmosphere and slowly removes lightweight particles that escape into space. This process is extremely slow, unfolding over billions of years, but it provides a glimpse into the chemical history of the planet. The loss of hydrogen suggests that Venus may once have had more water than it does today, possibly even shallow oceans that evaporated as the greenhouse effect strengthened. This slow escape continues quietly, shaping the long-term evolution of the atmosphere in a way that reveals how Venus transitioned from a potentially milder world to its current hot and dense environment. Near the cloud tops of Venus, temperatures decrease dramatically, creating a region where particles form stable, finely layered structures. These layers are composed of droplets and crystals that settle into thin sheets, each shaped by the balance between gravity, sunlight, and atmospheric motion. When studied through specialized imaging, these layers appear as soft, stacked bands that encircle the planet, marking altitudes where temperatures and chemical compositions stabilize. These cloud layers help regulate how heat moves between different heights in the atmosphere, contributing to the planet's overall thermal balance. Their orderly arrangement adds another quiet, structured element to the atmospheric system of Venus. The equatorial regions of Venus host areas where atmospheric waves converge, forming long, faint cloud structures that stretch across entire hemispheres. These features, sometimes described as planetary scale waves, move slowly around the globe and maintain their shape for extended periods. They influence wind patterns, cloud formation, and the distribution of chemical species within the atmosphere. The persistence of these waves demonstrates the organized nature of Venus's atmospheric circulation, where large-scale motions unfold gradually and maintain their integrity over vast distances. These structures show that the atmosphere is not simply chaotic, but is shaped by deep, stable patterns that guide its behavior. One extraordinary aspect of Venus's thick clouds is their ability to block nearly all visual access to the surface, requiring radar mapping to reveal the terrain below. This technique sends radio waves through the clouds, allowing them to bounce off the surface and return with information that can be transformed into detailed images. Over decades, missions such as Magellan mapped almost the entire planet using this method, revealing mountains, valleys, and plains invisible to traditional cameras. The surface of Venus remains hidden behind its permanent cloud cover, but radar allows scientists to see through this barrier in a gentle, non-disruptive way, uncovering the planet's geological features without altering the environment. The surface of Venus remains remarkably unchanged due to the absence of rain, rivers, or strong winds. While Earth's landscapes are reshaped continuously by weather and water, Venus's terrain experiences almost no erosion. As a result, geological features persist for extremely long periods, their forms preserved in the stillness of the planet's environment. Rocks and volcanic structures maintain their shapes without significant alteration, allowing scientists to study formations that have remained stable for millions of years. This lack of erosion creates a planet where the surface reflects deep geological time in a clear, uninterrupted way. Venus has a unique type of geological structure known as a pancake dome, wide, flat, volcanic formations that resemble shallow, circular disks. These domes are created when thick, viscous lava slowly emerges and piles up near the vent without flowing far. The result is a large, gently curved feature with smooth edges and a stable profile. Pancake domes are uncommon in the solar system, and their presence on Venus highlights the planet's distinctive volcanic processes. Their uniform shapes, broad extent, and slow formation contribute to the calm, stable character of Venusian geology. At the upper boundaries of the atmosphere, Venus interacts with the solar wind in a way that creates a long, faint atmospheric tail stretching behind the planet. This tail forms as charged particles from the sun push against the outer layers of the atmosphere, carrying some of the gases into space. The tail extends for millions of kilometers, but remains extremely diffuse, blending gradually into the surrounding environment. Although subtle, this feature demonstrates how Venus is connected to the solar system around it, with slow, continuous exchanges occurring between the planet and the space beyond. Near the terminator, the boundary between the permanent day side and the long night side of Venus, the atmosphere undergoes a gentle shift in temperature and airflow. Instead of experiencing sharp transitions, the change between light and dark unfolds slowly over a wide region where sunlight becomes increasingly diffused through thick clouds. In this zone, atmospheric currents adjust gradually, creating soft, layered motions as cooler gases meet warmer ones. The transition is so smooth that the boundary behaves less like a line and more like a broad, slowly shifting band encircling the planet. This gradual blending of day and night contributes to the overall stability of the Venusian climate, reinforcing the planet's signature uniformity. High in the atmosphere, around the cloud tops, Venus displays waves that span thousands of kilometers. One of the largest of these is a standing gravity wave observed by orbiters, a stationary feature that remains fixed over a specific region despite the fast-moving winds around it. This immense wave is believed to form when air flows over imbalances in the terrain far below, carrying atmospheric energy upward until it forms a stable, planet-sized pattern. Even though the winds rush past at great speed, the wave itself stays anchored in place, revealing a hidden connection between deep geological structures and upper atmospheric dynamics. Venus's atmosphere contains a persistent layer of haze beneath the main cloud deck. This haze extends deep into the lower atmosphere and is formed from extremely small particles suspended within the dense carbon dioxide. Because this region is shielded from direct sunlight by the thick clouds above, the haze scatters whatever light reaches it into a muted, uniform glow. This soft illumination helps maintain the planet's steady temperatures and prevents sharp thermal gradients. The haze layer acts as a buffer, smoothing out fluctuations and contributing to the planet's quietly balanced environmental structure. One of the most distinctive features on Venus is the presence of labyrinthine terrains, regions marked by a network of intersecting ridges and grooves. These complex patterns form through prolonged stretching, compression, and uplifting of the crust, creating a surface texture that appears intricately woven. Though visually striking, these terrains evolve slowly, shaped by forces deep within the planet over vast periods of time. Their interlocking structures provide clues about the unique tectonic behavior of Venus, where localized crustal movement creates long-lived features that remain preserved under stable atmospheric conditions. Some areas on Venus show evidence of volcanic domes that formed when steadily rising magma pushed upward but did not break violently through the surface. Instead, the crust gently bulged, forming rounded hills with smooth, symmetrical shapes. These uplifted structures reveal a style of volcanism that progresses without explosive activity, further illustrating the calm geological processes that dominate the planet. Over time, the domes remain intact due to the absence of erosion, allowing their shapes to be studied long after they form. The deep atmosphere of Venus is rich in carbon monoxide, produced when sunlight breaks apart carbon dioxide molecules in the upper layers. As this newly formed carbon monoxide sinks, it mixes with other gases and slowly participates in chemical reactions that help regulate the planet's atmospheric composition. The cycle is steady and continuous, reflecting the long-term chemical balance maintained throughout the atmosphere. This process unfolds quietly, shaping the chemical landscape of Venus without abrupt changes or disruptions. Radar studies have revealed regions on Venus where the surface appears unusually reflective at certain wavelengths. These bright patches may be caused by the presence of metallic frost, materials such as lead sulfide or bismuth sulfide that condense at cooler temperatures found at high elevations. Although not frost in the traditional sense, these reflective materials coat mountain ranges and uplifted areas, creating subtle brightness patterns visible only through specialized instruments. The presence of these substances suggests that Venus's atmosphere interacts with its surface in gentle but meaningful ways, depositing compounds that slowly accumulate over time. The crust of Venus is thought to undergo periodic cycles of weakening and strengthening due to heat trapped within the interior. As heat builds beneath the surface, the crust may soften and allow magma to rise in broad, gentle flows. Later, as this heat dissipates upward into the atmosphere, the crust stabilizes again. These thermal cycles occur on geological timescales, contributing to the large volcanic plains and shield structures seen across the planet. The repeated warming and cooling of the crust unfold gradually, shaping Venus's surface through slow, continuous change. In the upper atmosphere, Venus exhibits a faint glow known as air glow, a soft emission of light produced by chemical reactions high above the cloud layers. This glow is not visible from Earth without specialized instruments, but orbiters can detect it. The air glow reveals the interaction between solar radiation and atmospheric gases, creating a gentle illumination that emerges on the night side of the planet. Although subtle, this phenomenon shows that even in darkness, Venus maintains quiet activity driven by its atmospheric chemistry. The gravity of Venus is slightly weaker than Earth's, but strong enough to shape its atmosphere and solid surface in predictable ways. The reduced gravity affects how clouds form, how gases rise and fall, and how volcanic flows spread across the plains. It also influences the scale of geological features, allowing certain structures, like broad volcanic domes or long channels, to expand more widely than they would under Earth's stronger gravity. The balance between gravity, heat, and atmospheric density creates conditions unique to Venus, enabling slow, expansive formations that define much of the planet's landscape. Deep within the lower layers of Venus's atmosphere, temperatures rise to levels where many common materials would soften or melt. Yet the air remains so dense that motion progresses slowly and evenly. In this environment, gases settle into layered structures shaped by gradual convection rather than sudden turbulence. Hotter air gently rises, and cooler air descends in cycles that play out over long periods of time, forming a stable circulation pattern that supports the planet's uniform climate. These slow-moving currents demonstrate how Venus maintains balance despite its intense heat, with the atmosphere acting as a vast regulating blanket that distributes energy with remarkable consistency. Venus's crust contains expansive volcanic plains known as lava flood basalts, regions formed when low-viscosity lava spread widely across the surface before cooling. These plains extend for hundreds of thousands of square kilometers, covering older terrain beneath thick layers of basalt. The lava eventually cooled into smooth, open surfaces, broken only by occasional ridges or fractures. Because erosion is extremely minimal on Venus, these plains remain well preserved, allowing scientists to study large-scale volcanic events that shape the planet's appearance. Their sheer size and uniformity illustrate the magnitude of volcanic episodes that once defined the planet's surface. The atmosphere of Venus contains trace amounts of noble gases such as argon and neon, remnants of processes that date back to the planet's formation. The proportions of these gases provide clues about the early history of Venus, including how its atmosphere originally formed and how it has evolved over billions of years. The consistent ratio of these gases throughout the atmosphere indicates limited escape over time, revealing a stable environment where heavier gases remain largely confined. Studying these noble gases has helped researchers understand the deep past of the planet, offering insight into conditions that no longer exist. In the high-altitude cloud layers, Venus experiences a phenomenon known as downwelling, where cooler, denser air moves toward the lower atmosphere. This motion occurs as part of the planet's global circulation system and helps maintain balance between the super-rotating winds and the deeper, slower-moving layers. The downwelling process occurs gradually, forming smooth columns of descending air that stabilize the middle atmosphere. This continuous exchange ensures that chemical compounds, heat, and momentum flow throughout the entire atmospheric column, creating a cohesive system that functions without sudden disturbances. The surface of Venus exhibits patterns of faults and fractures created by long-term tectonic stresses within the crust. These features are not the result of plate boundaries like those on Earth, but instead emerge from the slow buildup and release of pressure within localized regions. The fractures often crisscross in geometric patterns, forming grids or branching structures that stretch for many kilometers. These tectonic networks reveal how the crust responds to internal forces over long periods, gradually adjusting to shifts in heat and pressure without dramatic movement. The consistency of these patterns provides evidence of a planet evolving through slow, steady geological processes. The chemical reactions occurring within Venus's dense atmosphere produce a variety of sulfur compounds, some of which contribute to the planet's distinctive yellowish-white appearance when viewed from space. These compounds form and break down through cycles driven by sunlight and atmospheric movement. Over time, they drift between cloud layers, combining with other particles to shape the reflective properties of the atmosphere. These chemical pathways operate with a quiet rhythm, continuously reshaping small details of the cloud composition without altering the overall stability of the atmospheric structure. Among the many geological features on Venus, rift zones are particularly striking. These elongated depressions form when the crust slowly stretches and thins, creating long valleys bordered by fractured terrain. Unlike Earth's rifts, which often widen over time and form new crust, Venusian rifts spread only modestly and remain relatively unchanged once formed. The stability of the crust prevents large-scale movement, allowing the rifts to maintain their appearance for extended periods. These features give scientists important clues about how Venus's interior releases heat and how the crust responds to underlying mantle activity. The upper layers of Venus's atmosphere contain a region where temperatures decrease enough for certain gases to condense slightly, forming a thin, stable layer of droplets that do not behave like typical clouds. This layer creates a narrow transition zone between the dense lower atmosphere and the more dynamic upper cloud decks. Its position remains relatively fixed, acting as a boundary that organizes how heat and chemicals move vertically. Although subtle in appearance, this layer plays a significant role in maintaining the planet's thermal gradient, helping to regulate the flow of energy through the atmospheric column. Venus demonstrates slow and steady loss of atmospheric oxygen, a process driven by ultraviolet radiation from the sun breaking apart carbon dioxide molecules. When this occurs, oxygen atoms are released but quickly recombine or escape the atmosphere altogether. Because the loss unfolds at a very gradual pace, it does not significantly alter the atmospheric balance over short timescales. However, the long-term trend provides valuable information about how Venus continues to evolve chemically. This steady escape of light elements reflects the planet's ongoing interaction with solar radiation in the absence of a strong magnetic field. At higher elevations on Venus, such as mountaintops and plateaus, temperatures are slightly cooler than in the surrounding lowlands, even though the difference is modest by Earth standards. These cooler regions allow for the condensation of certain metallic compounds that form reflective coatings on the surface. This process creates bright patches visible in radar images, marking areas where atmospheric chemistry interacts directly with the landscape. The subtle temperature variation between high and low terrain reveals how the atmosphere responds to changes in elevation, forming a gentle but consistent gradient across the planet's surface. Within the dense atmosphere of Venus, sound travels differently than it does on Earth. Because the air is so thick, sound waves move more efficiently, spreading through the lower layers with greater speed and intensity. A sound that would dissipate quickly on Earth would carry farther on Venus, though the high temperature and pressure would influence how the sound is perceived. This enhanced transmission creates an environment where vibrations linger slightly longer, and where waves of pressure move with a steady, uninterrupted flow. Although the surface is silent today, The physics of sound on Venus reveal an atmosphere capable of carrying audio in a smooth, amplified manner, unlike anything experienced on our own planet. Deep radar observations have revealed long channels that once carried slow-moving lava across the surface. Some of these channels stretch for thousands of kilometers, making them the longest known volcanic conduits in the solar system. Unlike rivers formed by flowing water, these channels were shaped by molten rock that traveled gradually across open terrain. Their smooth, continuous paths show that the lava maintained a consistent temperature and viscosity over great distances. The scale of these channels reflects the planet's ability to support long-lived volcanic flows, shaping the landscape with processes that unfolded in quiet, sustained motions rather than abrupt eruptions. Venus's rotational axis is tilted only slightly relative to its orbital plane, creating almost no seasonal variation. This minimal tilt means that sunlight reaches each part of the planet with nearly identical intensity throughout the year. As a result, Venus experiences no significant changes in temperature or atmospheric behavior based on seasonal cycles. The lack of seasons contributes to the planet's uniform thermal environment, allowing temperatures and pressures to remain constant over long periods. This stability reinforces the sense of timelessness that defines Venus, where the passage of a year brings almost no difference to the planet's climate. In the cloud layers above Venus, chemical reactions driven by sunlight produce a continuous cycle of sulfuric acid droplets. These droplets form when sulfur dioxide interacts with water vapor and ultraviolet radiation, creating stable particles that populate the dense cloud decks. Over time, gravity pulls some droplets downward, where they evaporate and release their components back into the atmosphere. The cycle then begins again as new droplets form in the upper layers. This repeating process operates with steady continuity, shaping the optical properties of the clouds and maintaining their reflective nature. It is one of the most persistent and organized chemical cycles anywhere in the solar system. Infrared observations of Venus reveal patterns of thermal emission that shift gradually across the cloud tops. These emissions highlight areas where heat escapes more efficiently or where atmospheric motion influences the temperature distribution. Although the differences are subtle, they create gentle gradients that help scientists understand how energy flows across the upper atmosphere. These thermal patterns demonstrate that even at high altitudes, where winds move rapidly, the atmosphere maintains a structured balance between heat, motion, and radiation. The slowly varying thermal signatures contribute to the planet's overall calm and measured behavior. The crust of Venus contains large fracture belts that stretch across the plains in long, winding patterns. These belts are formed when the crust responds to stresses deep within the planet, creating networks of cracks that propagate over great distances. Unlike tectonic boundaries on Earth, these fracture belts do not separate plates, but instead reflect internal adjustments within a single, continuous crust. Their formation occurs over millions of years, with pressure building gradually until the crust yields in slow, controlled movements. The resulting structures show a planet shaped by internal forces that act predictably and patiently, creating features that remain stable under the weight of the dense atmosphere. Venus's dense atmosphere scatters sunlight so effectively that visibility on the surface is limited even during the brightest part of the day. Instead of sharp shadows and bright illumination, the surface receives a diffuse, amber-colored glow that permeates the air from all directions. This diffused lighting softens the entire landscape, reducing contrast and making the horizon appear hazy. The uniform glow creates a muted environment where brightness changes slowly and evenly, further reinforcing the calm, timeless quality of the planet's surface conditions. At high altitudes, the winds that sweep around Venus generate subtle temperature variations that reveal the underlying structure of atmospheric circulation. These variations help define large-scale patterns, such as the Hadley cells, which transport heat from equatorial regions toward the poles. The circulation system on Venus operates with a smooth, continuous flow, guiding air upward near the equator, distributing it across the cloud tops, and returning it toward the surface at higher latitudes. This gentle but powerful pattern is one of the core reasons why Venus maintains such uniform temperatures across its surface, providing a mechanism for heat to move efficiently throughout the atmosphere. Venus occasionally exhibits faint lightning-like activity within its cloud layers. While not identical to lightning on Earth, these flashes are believed to result from electrical discharges produced by collisions between sulfuric acid droplets or by interactions within turbulent upper cloud regions. The events occur sporadically and are often subtle, detected through instruments rather than visible light. Their presence indicates that even in a world defined by stability and uniformity, small-scale electrical processes contribute to the planet's atmospheric behavior. These discharges unfold quietly, leaving no long-term impact on the clouds, yet adding a layer of complexity to the atmospheric system. The atmosphere of Venus contains a stable boundary known as the tropopause, a layer where temperature gradients shift and atmospheric motion transitions between the lower and upper systems. This region forms a smooth separation between the hot, dense lower layers and the cooler, dynamic upper clouds. The tropopause remains at a consistent altitude across the planet due to the uniform temperature profile. It acts as a regulating layer, shaping the flow of heat and chemicals between different atmospheric zones. The consistency of this boundary highlights the structured balance of Venus's atmosphere, where transitions occur gently rather than abruptly. In the deep atmosphere of Venus, the immense pressure affects the behavior of gases in ways not seen on Earth. Carbon dioxide, which makes up most of the atmosphere, becomes so densely compressed that its physical properties begin to shift toward those of a supercritical fluid. In this state, the distinction between liquid and gas becomes less defined, allowing the atmosphere to hold and transport heat with remarkable efficiency. This dense environment enables energy to move smoothly through the lower layers, creating a thermal stability that contributes to the planet's consistent temperatures. The slow, uniform movement of this supercritical mixture reveals the extraordinary influence of pressure on the physics of Venus's atmosphere. The surface of Venus is dotted with structures known as shield fields, broad regions where multiple volcanic vents have produced overlapping lava flows. These fields consist of numerous low-profile volcanic features arranged closely together, forming expansive, slightly raised surfaces. Unlike volcanic fields on Earth, which often show sharp boundaries or varied elevations, the shield fields on Venus blend gently into surrounding plains. This smooth integration reflects the planet's low erosion rates and the slow, steady manner in which volcanic materials settle and solidify. Each shield field records a long history of volcanic activity that unfolded quietly over extended geological periods. Deep radar mapping has revealed ridge belts on Venus' narrow, elongated regions where the crust has been compressed into parallel ridges. These features form when internal forces push the crust together, causing it to fold upward in repeated patterns. The ridges often stretch for hundreds of kilometers and maintain remarkably consistent spacing, reflecting the uniform nature of stress within the crust. Their formation does not involve rapid movement, but instead arises from steady internal pressure, acting over immense timescales. The orderly structure of ridge belts provides evidence of a planet shaped by long, patient cycles of compression and uplift. Venus's upper cloud layers contain particles that scatter ultraviolet light differently than visible light, producing contrasting patterns when viewed through specialized instruments. These ultraviolet contrasts reveal motions and structures that remain invisible at other wavelengths, allowing scientists to trace the pathways of atmospheric currents. The patterns shift gradually over time as winds redistribute the absorbing particles across the cloud tops. This ultraviolet perspective provides a unique view of the dynamics within the upper atmosphere, showing how complex chemical and physical interactions create subtle, slowly evolving textures across the planet's cloud deck. Many volcanic features on Venus display signs of interaction between rising magma and the overlying crust, forming structures known as steep-sided domes. These domes are unusual because they contain lava that is likely thicker and more viscous than typical basaltic flows. As the dense lava emerged, it accumulated near the vent, creating dome-like formations with steep, rounded slopes. Their shapes remain well preserved due to the lack of weathering, allowing scientists to study their formation in detail. These domes provide insight into the composition of Venus's interior and demonstrate the diversity of volcanic processes shaping its surface. In certain regions of Venus, large crater-like depressions, known as arachnoids, appear in patterns that resemble delicate, web-like structures. These features form through a combination of subsurface intrusion and surface collapse, creating circular or oval shapes intersected by radiating fractures. Their formation occurs slowly as pressure builds beneath the crust, eventually causing the surface to sag and crack. Arachnoids are unique to Venus, and their intricate shapes highlight the planet's distinctive volcanic and tectonic behavior. Their patterns remain preserved under the stable atmosphere, creating geological records that endure for vast spans of time. The distribution of impact craters on Venus reveals important clues about the age of the planet's surface. Because the atmosphere is thick enough to burn up smaller objects before they reach the ground, only larger meteors create craters. These larger impacts are relatively rare, and their even distribution across the planet suggests that the surface was resurfaced globally in the past. Since that event, the low rate of impacts has resulted in a surface that shows few signs of modification. The stability of crater distribution indicates a planet where major geological changes occur infrequently, preserving the surface's structure with exceptional clarity. The middle atmosphere of Venus contains regions where chemical reactions produce small amounts of chlorine and other halogens. These elements form through high-energy processes driven by ultraviolet radiation and interactions with sulfur-bearing compounds. Although present in trace amounts, these chemicals contribute to the long-term evolution of the atmosphere and help regulate the balance of other gases. Their presence demonstrates the complexity of Venusian atmospheric chemistry, where a wide range of reactions continues quietly within the dense layers, shaping the planet's environment in subtle ways. The temperature profile of Venus shows a gradual decrease with altitude, creating a stable, vertical structure that prevents sudden atmospheric mixing. This stability allows thermal gradients to remain consistent across the planet, producing predictable layers that guide wind patterns and chemical processes. The smooth decline in temperature from the surface upward ensures that the atmosphere remains stratified, with each layer operating under its own steady conditions. This stratification contributes to the overall calmness of the Venusian environment, supporting long-lasting atmospheric patterns that rarely experience rapid shifts. Venus's interaction with the solar wind creates a bow shock, a region where the flow of charged particles slows rapidly as it encounters the planet's atmosphere. Despite lacking a strong magnetic field, Venus generates an induced magnetosphere through the movement of charged particles around the upper atmospheric layers. This interaction forms a protective boundary that shields the planet from some of the solar wind's energy. The bow shock remains relatively stable, with its position shifting only gradually in response to changes in solar activity. This induced magnetosphere highlights how Venus adapts to the solar environment, using atmospheric processes rather than internal magnetism. The atmosphere of Venus contains a region where carbon dioxide begins to dissociate under the influence of strong ultraviolet radiation from the sun. This process occurs gradually in the upper layers, where lower pressure allows sunlight to penetrate more deeply. As the molecules separate, they produce carbon monoxide and oxygen atoms that drift and react with nearby particles before eventually recombining. This continuous cycle of dissociation and recombination forms one of the most stable chemical loops on Venus, contributing to the long-term maintenance of atmospheric composition. Because it unfolds at such a slow and measured pace, the cycle reinforces the quiet, steady evolution of the planet's upper atmosphere. In the deeper layers of the clouds, droplets of sulfuric acid form dense concentrations that settle slowly downward before evaporating. This evaporation releases water vapor and sulfur dioxide back into the atmosphere, enabling the formation of new droplets higher up. The entire cycle resembles a vertical transport mechanism, operating through gentle rise and fall, driven by temperature changes between altitudes. This vertical movement helps maintain the structure of the cloud decks, ensuring that each layer remains distinct while still participating in the planet's overall circulation system. It is a delicate, continuous process that supports the reflective nature of Venus's atmosphere. Some regions of Venus reveal signs of ancient lava channels that appear to have interacted with obstacles in the terrain, creating branching pathways that extend outward from their original flow lines. These interactions show how molten rock navigated around uplifts, ridges, and slight depressions, shaping complex patterns that remain preserved today. Because erosion is minimal, these branching structures offer a clear record of how lava behaved as it cooled, spread, and adapted to surface variations. Their intricate shapes provide a window into the planet's volcanic past, demonstrating processes that advanced with patience and consistency. The upper atmosphere of Venus contains layers where wind shear the gradual change in wind speed, with altitude forms subtle boundaries separating different airflow regimes. These boundaries do not create sudden turbulence, but instead allow the atmosphere to transition smoothly from slower currents below to the fast-moving super-rotation above. As each layer shifts into the next, the flow of gases aligns into stable motions that repeat over long periods. The existence of these boundaries reveals the highly structured nature of Venus's atmosphere, where movement unfolds in controlled, predictable gradients rather than abrupt transitions. Radar imaging has shown that some mountain slopes and elevated regions on Venus have directional textures formed by prolonged interaction with atmospheric particles. Over time, tiny grains carried by gentle surface winds move in consistent patterns, gradually shaping the orientation of small-scale features. Although the winds near the surface are slow due to the dense atmosphere, the particles still drift with enough force to leave subtle imprints on the terrain. These directional markings form over immense spans of time, offering evidence that the lower atmosphere, though calm, still participates in shaping the surface in fine, deliberate ways. In certain equatorial regions, scientific observations reveal thermal anomalies that suggest slight differences in surface emissivity, the ability of the terrain to radiate heat into the atmosphere. These variations are tiny but detectable, indicating that some rocks and minerals emit heat more readily than others. Because Venus lacks strong daily temperature cycles, these emissivity differences reflect intrinsic surface properties rather than environmental changes. The gentle contrast between materials offers clues about the mineral composition of the planet's crust, helping scientists understand the diversity of volcanic products that once shaped the plains. High above Venus, in the ionosphere, charged particles interact with solar radiation to create layers that expand and contract slowly over time. These changes occur in response to variations in solar activity, yet the overall structure of the ionosphere remains remarkably stable. This region helps regulate the escape of particles from the atmosphere and forms part of the induced magnetic environment surrounding the planet. The slow, regular breathing of the ionosphere, expanding under stronger sunlight and contracting when conditions calm, adds another element of rhythm to the planet's atmospheric system. Venus exhibits subtle variations in atmospheric density across different latitudes, shaped by small differences in heating from the sun and the gradual redistribution of energy by the winds. Although the planet is known for its uniform climate, these gentle density gradients help drive long-distance circulation patterns that connect the equator to the poles. The contrasts are faint, but they play a role in determining where clouds thicken, where winds accelerate, and how gases move throughout the atmosphere. These quiet variations highlight the complexity of a system that appears simple on the surface, but contains finely tuned layers of internal motion. Surface emissivity measurements also reveal regions where volcanic rocks retain slightly different thermal signatures, hinting at varying ages across the terrain. Younger regions cool differently than older ones due to subtle differences in texture or composition. Because Venus undergoes little erosion, these differences persist for long periods, offering insight into the timing of past volcanic activity. By mapping these regions, scientists can identify areas that resurfaced more recently in geological history, helping reconstruct the timeline of the planet's evolution. The ionosphere of Venus occasionally forms pockets where electron density changes in smooth, wave-like patterns. These structures drift slowly across the planet, shaped by interactions between solar radiation and the magnetic environment induced by the atmosphere. Though invisible to the eye, they reveal the upper atmosphere's calm response to changing solar conditions. These waves move without abrupt disruptions, reflecting the gentle, controlled nature of Venus's atmospheric layers even at high altitudes. In the lower atmosphere of Venus, carbon dioxide absorbs and re-emits infrared radiation continuously, creating a deep thermal reservoir where heat moves slowly through dense layers of gas. This constant absorption and release of energy forms an environment where the temperature remains uniform across wide areas, even in regions far from the planet's hottest zones. The slow radiative transfer ensures that the atmosphere retains warmth efficiently, supporting the persistent greenhouse effect that defines Venus. This steady, repeating cycle highlights the planet's ability to maintain a thermal balance without dramatic fluctuations, shaping a world where temperature behaves in a calm, predictable manner. Radar studies have identified fracture zones on Venus that stretch across the surface in curving, interlocking patterns. These zones, formed through long-term deformation of the crust, create networks of cracks that remain stable under the intense pressure of the atmosphere. The fractures do not widen rapidly or collapse, but instead shift slowly as the crust adjusts to heat from the interior. Over millions of years, these zones have maintained their shapes, offering a detailed record of tectonic stress and crustal response. The gradual development of fracture systems shows how Venus expresses internal forces through gentle structural changes rather than abrupt movements. At certain altitudes within the cloud layers, particles align into stable haze structures that form consistent patterns around the planet. These structures mark regions where atmospheric chemistry, temperature, and solar radiation interact in predictable ways. The haze layers remain suspended for long periods due to the constant upward and downward motion of air that balances pressure across altitudes. Their persistence reveals the controlled dynamics of the Venusian atmosphere, where conditions allow delicate equilibrium to form and remain intact over time. Venus's surface heat loss occurs almost entirely through radiation, rather than convection or conduction. Because the atmosphere is so dense, very little thermal energy escapes directly through contact with the air. Instead, the surface radiates heat upward, where it is absorbed and redistributed by carbon dioxide. This slow radiative cooling contributes to planet's uniform temperature profile, preventing any sudden drops in heat across the landscape. The steady process allows Venus's surface to maintain long-term thermal stability, even in areas that have cooled from ancient volcanic activity. Magellan's spacecraft data revealed subtle variations in microwave emissivity across the surface of Venus, suggesting differences in mineral composition among volcanic plains. These variations provide clues about different lava types and cooling rates, which help reconstruct the planet's volcanic history. Because erosion is minimal, these emissivity signatures remain clear indicators of geological diversity. The consistent preservation of surface materials allows researchers to trace chemical differences across vast regions, revealing a landscape shaped by multiple styles of volcanism over time. In the mid-atmosphere, Venus hosts regions where wind speeds shift gradually between layers, creating smooth shear zones that define the structure of atmospheric motion. These zones allow air from different heights to interact in a controlled manner, supporting the superrotation above while stabilizing the slower winds below. The alignment of these shear layers creates a balanced system where energy transfers vertically in predictable ways. This slow, organized interaction between layers is a core element of the atmosphere's long-term stability. Venus's ionosphere contains a region where solar radiation ionizes carbon dioxide into charged particles that drift along the upper atmosphere. These particles accumulate into layers whose density changes gently with local time and solar activity. Although the variations are subtle, they form consistent daily cycles that influence how the atmosphere interacts with the solar wind. The smooth pattern of ionization and recombination demonstrates the controlled response of Venus's upper atmosphere to sunlight, revealing processes that repeat without abrupt disturbances. The thick cloud layers of Venus reflect nearly all sunlight that reaches them, preventing direct illumination from reaching the surface. Despite this, thermal imaging reveals a slow transfer of heat through infrared wavelengths that pass more easily through the lower atmosphere. This selective transparency allows certain wavelengths to travel upward from the surface, while others remain trapped below. The process unfolds gradually and is a key factor in maintaining the planet's internal heat balance. It contributes to the deep thermal consistency that characterizes Venus from its plains to its highlands. Some regions of the surface contain tessera terrain areas with complex, intersecting ridges that form geometric patterns unlike any other planetary geology. These terrains result from repeated cycles of crustal deformation involving uplift, compression, and folding. Their intricate structure indicates a long and active geological past that predates much of the planet's volcanic resurfacing. Despite their ancient age, tessera regions remain well preserved, protected by the planet's minimal erosion. Their survival offers a rare glimpse into the earliest chapters of Venus's evolution, captured in stable, unmoving patterns. High-altitude clouds on Venus contain finely layered structures shaped by temperature gradients and atmospheric waves. These layers stretch around the planet, forming continuous bands that remain aligned with global circulation patterns. The cloud layers rise and fall gently, depending on local pressure changes, creating a quiet, vertical motion that adds depth to the atmospheric system. The stability of these layers illustrates how Venus's atmosphere organizes itself into ordered zones that maintain their structure over time, even as high-speed winds move around the planet. In the deep cloud layers of Venus, small droplets coalesce into larger particles before eventually separating again as they rise or fall through the atmosphere. This continuous merging and splitting forms a quiet, microphysical cycle that influences the reflective properties of the clouds. Because the process occurs slowly and consistently, the particles maintain a stable size distribution, which contributes to the planet's high albedo. The equilibrium between droplet formation, growth, and evaporation is delicate but enduring, shaping the cloud's behavior without dramatic fluctuations. This predictable cycle is a key factor in the uniform brightness of Venus when viewed from space. The surface of Venus shows evidence of ancient volcanic plateaus created by repeated lava flows that built up layers over time. These plateaus rise subtly above the surrounding plains and contain smooth surfaces that extend over large areas. Their formation required long intervals of volcanic activity, where lava emerged gradually rather than explosively. Because the environment produces little erosion, these plateaus have retained their form for millions of years, offering a preserved record of the planet's volcanic history. The layered nature of the plateaus reveals how Venus resurfaced itself through gentle but sustained outpourings of molten rock. In the mid-latitude regions of Venus, radar imaging reveals subtle variations in surface roughness. These patterns reflect differences in how lava cooled and solidified after spreading across the plains. Some areas display finely textured surfaces that scatter radar waves differently from smoother regions nearby. These variations help scientists analyze the composition and age of volcanic formations, offering insights into the timing and style of past eruptions. Because the atmosphere shields the surface from erosion, these textural differences remain clear and stable, forming a natural archive of geological conditions. The high atmosphere of Venus hosts energetic particles that enter from the solar wind and interact with atmospheric gases. These interactions create narrow layers where ions accumulate before gradually dispersing. Although these layers are invisible to the eye, instruments detect their steady formation and dissolution, revealing the atmosphere's response to changing solar conditions. The slow, wave-like behavior of these ion layers demonstrates how the upper atmosphere absorbs and redistributes solar energy in a smooth, controlled manner. This interaction plays a role in shaping the planet's induced magnetosphere. Venus's crust contains regions where uplifted highlands meet surrounding plains in gentle transitions rather than steep boundaries. These slopes formed through slow geological processes where internal pressure caused the crust to rise without creating abrupt cliffs. Over time, volcanic activity and thermal changes smoothed these transitions even further. The result is a landscape with gradual shifts in elevation, where large-scale features blend seamlessly into one another. This gentle topography reflects the planet's tendency toward slow, long-term change rather than sudden geological events. Near the polar regions, temperature gradients between different layers of the atmosphere create broad circulation cells that help redistribute heat from the equator toward the poles. These cells move air downward near the poles and upward near the mid-latitudes, forming a stable pattern that supports the overall energy balance of the planet. The motion occurs at a steady, measured pace, contributing to the uniform temperatures observed across the globe. This polar circulation system is an essential component of Venus's stable atmospheric structure. Some of the oldest terrains on Venus contain cross-cutting features where younger volcanic flows partially cover older tectonic structures. These relationships reveal the sequence of geological events that shape the landscape. Because erosion is minimal, the boundaries between old and new formations remain sharp and informative. Scientists can trace how volcanic resurfacing interacted with pre-existing faults, ridges, and domes, reconstructing a timeline of planetary development. The clarity of these overlapping structures demonstrates the remarkable preservation of geological history under Venus's stable conditions. In certain regions, atmospheric temperatures align with the freezing points of specific minerals, causing them to precipitate out of the atmosphere and adhere to high elevation surfaces. These precipitated minerals create reflective coatings that show up clearly in radar observations. Their presence indicates a direct interaction between atmospheric chemistry and topographical features, where elevation plays a role in determining which compounds stabilize on the surface. This process unfolds slowly, allowing materials to accumulate over long periods and form distinct highland signatures. The atmosphere of Venus contains long-lived patterns known as planetary scale waves that influence global circulation. These waves propagate through the cloud layers in smooth, repeating motions that remain stable despite the strong winds surrounding them. They help regulate the distribution of temperature and chemical compounds across the planet, forming a framework for atmospheric dynamics. The persistence of these waves highlights the organized nature of Venus's circulation system, where even large-scale motions follow predictable rhythms. At the highest altitudes, Venus's atmosphere transitions into a thin exosphere where particles escape into space. This region is extremely diffuse, with molecules drifting apart slowly as they reach escape velocity. The loss of atmospheric particles occurs at a gradual pace, shaped by interactions between solar radiation and the induced magnetosphere. Although the rate of loss is small, it represents the final stage in the planet's long-term atmospheric evolution. The slow escape of particles into space completes the cycle of energy and motion that defines Venus's upper atmosphere. As our quiet journey through the world of Venus reaches its end, allow your mind to rest in the calm rhythm of everything you've heard. Venus is often described as extreme, but when explored with patience, it reveals a deeper truth, a world governed not by chaos, but by long cycles, slow transitions, and structures that persist unchanged for millions of years. In every layer of its atmosphere, in every curve of its landscape, Venus moves at a pace that feels almost timeless. Nothing rushes, nothing interrupts. The clouds rotate with steady purpose, the surface evolves with immense patience, and the atmosphere reshapes itself through processes that repeat gently, again and again, without abrupt change. In learning about Venus, you've stepped into a place where the passage of time stretches far beyond ordinary experience, The slow rotation, the stable temperatures, the preserved landscapes, all of them form a world that exists in a continuous state of quiet balance. Even in its heat and density, there's a softness to Venus, a smoothness in the way its environment unfolds. Understanding this world reveals not only the science behind a neighboring planet, but also the beauty of stability, of steady movement, and of long-term calm. As you drift towards sleep, let your thoughts move at the same measured pace that defines Venus. Allow the quiet persistence of its atmosphere, the gentle curvature of its landscapes, and the unbroken flow of its winds to settle softly within you. There is a peaceful rhythm in the way Venus exists, and tonight you have followed that rhythm from its luminous cloud tops to the deep layers of its atmosphere. Thank you for joining the Sleepy Scientist. May your night be calm, your dreams unhurried, and your rest as steady and serene as the quiet world we explored together. Good night.